All right, this is your weekend lecture for Algebra 2, Semester 2. All right, so for this weekend, we're going to cover 4 units. That way, Monday is a little bit easier for us. Okay, so for today, we're going to cover 2.4, 2.5, 2.6, and 2.7. Okay, so that's what we're going to try to cover for this weekend here. Again, remember, if you fall behind, not the biggest deal, but again, try to keep up with us. All right, so if we start here with 2.4, we're looking at rationalizing denominators, right? Rationalizing denominators. So let's take a look at what that means here. All right, so far in this unit, apologies, so far in this unit, we've been working a lot with these rational expressions, right? Looking at multiplying, dividing, adding, subtracting, right? All of those basic functions here. All right, but we haven't worked with terms like we see here, this 5 over square root of 3. Okay, this 5 over square root of 3. All right, this right here shows a radical in the denominator, right? And then the top part is not a radical itself. All right, so in general, when we're dealing with something like this, it's easiest if we don't have that radical in the denominator of our fraction, right? So in order to do that, what we're going to have to do is we're going to have to multiply our number by a helpful fraction in the form of 1, right? And what that means is you're going to multiply by the same thing on top and on bottom. So essentially, it's like you're multiplying by a factor of 1. All right, so let's look at what that means here. All right, and this is the process called rationalizing the denominator. It's turning it into a rational number, right? Hopefully that makes sense here. We're trying to rationalize or turn the denominator into a rational number. All right, so if we look here, 5 over square root of 3. So we can do this thing where we multiply by square root of 3 over square root of 3. And again, the reason that is because square root of 3 over square root of 3, if I were to divide these out, this is just multiplying by 1. It's multiplying by a factor of 1. So if I multiply there, right, I can then calculate. And what happens is if I have square root of 3 multiplied by square root of 3, remember, we know that that just turns into the number underneath the radical symbol or the radicand, right? So this is going to turn into 5 times square root of 3 over 3, right? We get rid of that radical symbol in both of them, and we just are left with our original radicand. All right, and again, right here it says, why can you multiply by the square root of 3 over the square root of 3? Because again, essentially that's multiplying by a factor of 1. It's multiplying by a factor of 1 because square root of 3 divided by square root of 3 gives us 1. All right, and the reason this helps is because it gets the radical out of the denominator. It puts it in the numerator for us. All right, so it makes it easier for us to deal with. All right. So again, keeping in mind rationalizing the denominator is necessary because if we divide by an irrational number, it's much more complicated. All right, so if we look here at these two fractions, if I had 5 divided by square root of 3, all right, again, you're now having to divide 5 by this 1.7 value because square root of 3 is about 1.7, right? The square root of 3 is about 1.7. So it gets a little bit more tricky here when we're trying to do this division. Versus, if I'm trying to divide 3 by 5 square root of 3, right? 5 square root of 3 is about 8.6, okay? And we can divide this a lot nicer than this guy here. And as you're going to notice, it ends up with the same answer, 2.8, 2.8, right? It ends up with the same answer. This is just a much more easier process for us, all right? So again, in general terms, you can multiply the expression by b over b, where b is the denominator of the original expression. Again, this works because b over b is equal to 1. All right? Because b over b is equal to 1. All right, so this is, again, called rationalizing the denominator. All right, multiplying the numerator and denominator by the original value of the denominator, right? And again, in this expression, it's going to be value of b. So if we look at our example here, 3 over square root of 2x, 3 over square root of 2x, okay? I can multiply by by my original denominator. Same thing, it's 2x, all right? So I'm going to have square root of 2x over square root of 2x. Again, remember, multiplying by two of the same radicals are going to cancel out the radical, and on the bottom, I'm just going to be left with the 2x, all right? So again, this turns my original expression from 3 over square root of 2x to 3 times square root of 2x over 2x, all right? Another example here. Again, same thing. The entire thing is under the radical symbol. Okay, so you have to multiply by the entire radical. All right, so you're going to multiply both sides by x minus 1, and I'm going to calculate that out. All right, and again, not hopefully too difficult. You're just doing some basic multiplication here at this point. All right, and again, realizing that when I multiply two radicals together, it gets rid of that radical symbol as long as it's the same value. All right. So then here, if we have to deal with a radical on the denominator, but there's more than just one term, right? There's two terms here. All right, we can't just, unfortunately, use the same strategy of multiplying by the same number, because if we look at 5 plus square root of 3, if I multiply by 5 plus square root of 3 over 5 plus square root of 3, all right, when we calculate this out, we're basically doing a FOIL here, right? We're going to do a FOIL here. And when we end up simplifying here, it doesn't make it much nicer, right? The denominator is still irrational. It's still irrational. So we did not rationalize this denominator. It's still a difficult fraction for us to work with. So a new strategy that we're going to learn here is if I have two numbers, right? If I have two numbers, two values, I have to multiply my denominator by its conjugate, right? Remember, hopefully we remember this, right? Conjugates. So it's when we had a plus b and we had a minus b, right? A plus b and a minus b, right? We were talking about our binomial expressions. They're identical except for the sign between them, right? The sign between them. So what we're going to have to do here is we're going to multiply still b over b, but now instead of b being our original, it's going to be our conjugate of the denominator. It's going to be the conjugate of our denominator. All right, so if we look here, we've got 5 plus square root of 3. So our conjugate for this one is going to be 5 minus the square root of 3. 5 minus the square root of 3. All right, and when we calculate this out here, we're left with 25 minus 3. All right, and again, hopefully you can take my word for it, but you can also always solve this out here. Again, remember, we're just doing basic FOIL, right? So if you take these as two factors, right, this 5 plus square root of 3 and this 5 minus square root of 3, all you're doing is FOILing. So 5 times 5 gives us this 25 here. Now 5 times minus square root of 3, we're going to leave that because the next one here is 5 plus or plus 5 square root of 3. So those values cancel each other out, and then the only thing I'm left with is square root of 3 times square root of 3, which gives me this value of 3 here. All right, so again, all you have to do is FOIL this guy out to see that it works, and it's left with 25 minus 3. All right, and then of course we can simplify that down further, so we do, and we're left with 22 there. All right, we're left with 22. Okay, so obviously, then we know that we'd have to take the top and distribute that 2 there, but that's for a later date here, okay? So right now we're just looking at, we've rationalized the denominator here. We've rationalized the denominator. Okay, so again, when we have something with multiple factors, you're going to have to multiply by its complex conjugate. All right, again, more examples here. But in general, remember, look, if I have a plus b and a minus b, I'm left with a squared minus b squared, right? That's one of those tricks we learned when we were dealing a lot with quadratics. All right, and again, a lot of these are good examples here. But again, with any of these, if I look at maybe this one down here for my variables, right? I've got 1 times 1, 1. I've got 1 times negative x root 2. Okay, and then I've got 1 times by the positive values. That gives me this plus here. And then I've got the last two terms multiplied together, right? So I'm left with negative 2x squared. I'm left with negative 2x squared. So then again, I can cancel out those middle terms, and I'm left with just this final term here. Right, I'm left with just this final term. Okay, so you can take a couple minutes here on your own and look through these and really digest them. All right, but if we keep moving forward here, there's plenty of examples of looking at the complex conjugate to rationalize the denominator. So again here, I'm going to multiply by its complex conjugate. So square root of 5 plus 2, right? When I calculate those out, those are the values that I get. So then I can obviously simplify, and I would again simplify out the top, except for before I do that, there's another step that I can take here, which is dividing out any common terms. Dividing out any common terms. So for example, before I distribute this 3 here, look, I've got 3 and 6, okay? Well, there's a common term of 3 between both of these. So I can divide that 3 out, and I'm left with just 2 in my denominator. Right, so before I distribute out that value, okay, it's always good to see if you can divide. All right, so again here, 3 plus square root of 6, I calculate that guy out. All right, and then I'm left with 9 minus 6, which gives me 3. All right, and there is no common term that I can divide out by. So what I would do is I would multiply both of these factors by 2 here. All right, so this would be 6 plus 2 square root of 6 on top. All right, another example here. All right, so calculating that out, I'm left with x. I'm left with x minus 1 on bottom. And then again, I would distribute that x on top there. All right, and final example, same thing. Complex conjugate, multiply out, and then simplify if necessary or possible. All right, so then again, moving forward here, if I have 2 variables in the denominator, guess what? I'm going to use the exact same process here, okay? I'm just going to use the conjugate of my denominator still, all right? And I can do that with 2 radical terms. All right, so first off, step 1, multiply the numerator and denominator by the conjugate of the denominator. So the conjugate for this would be square root of x plus 2. Instead of this minus symbol here, it's going to be a plus square root of x. Right, so I multiply. All right, and I know it's not looking as nice here, all right, but it will, I promise. All right, so when we calculate the product, we do our FOIL process here. Right, we are left with x plus 2 times x plus 2, which gives me obviously just x plus 2, and then x and x, that gives me a minus x here. All right, and if we click on the denominator here, we can see, of course, if we FOILed it out, right, that's what we would be left with. All right, that's what we would be left with. All right, but from here, I can simplify. All right, from here, I can simplify because I had x minus x, so I'm left with 2. Okay, for this guy, I can factor out or divide out a number of 2 on the top and the bottom, so I'm just left with square root of x plus 2 plus square root of x. All right, believe it or not, it boils all the way down just to this value here. All right, so again, sticking with it, hopefully not anything too difficult. Again, it's just keeping track of what you're doing and making sure you're following all the processes here. All right, so then just to confirm what we know, you should not leave a radical in the denominator of a fraction. All right, you should not leave a radical in the denominator. Again, there's multiple steps here for how to get the radical out. And again, it's multiplying by a factor of 1. So whether it's b over b, where b is just the original radical, or if it's the conjugate, right, we're going to still multiply by that b over b in order to cancel it out. All right, so couple questions here. If we look at 9 minus square root of x plus 2, okay, the conjugate for this is going to be the same values, but again, the only thing we're changing is that plus sign instead of a negative. All right, so being really careful here, the answer is D. It's got to be 9 plus square root of x plus 2, right? This one here is not correct because it's x minus 2. All right, looking at this here, when you rationalize the denominator of the fraction, what is the new denominator? All right, so the new denominator here, we'd have to multiply by our conjugate, okay? So we're going to multiply by 3 minus square root of 9, right? 3 minus square root of 9. And if we remember, right, those middle terms when we FOIL out are going to cancel. So I'm going to be left with a squared minus b squared. So this is actually going to be a squared minus b squared. All right, so I'm going to be left with 3 squared minus 7. 3 squared minus 7. So I'm going to be left with 9 minus 7, which is going to give me a value of 2 here. All right, and then I'll leave 3 and 4 for you guys to try on your own here. All right. Same thing with this guy. All right, so with looking at some of these questions, which choice is the conjugate of the expression in the box below? Remember, it's the same exact values for A and B. You just have a opposite sign between them. All right, and something I do want to point out is they're doing a really good job of saying, okay, right, as long as x is greater than or equal to 3, right? Because we don't have the ability to take the square root of a negative number at this point, right? Square root of negative numbers are not real, so we don't take them. All right. Same thing here. Okay, again, remember, you're going to multiply by its complex conjugate. All right, FOIL that out, or just know that you're going to get a squared minus b squared and simplify, right? Simplify is going to be the key there. All right, same thing here. Rationalize the denominator for the fraction and then simplify. Okay, so being able to multiply by the complex conjugate, making sure you're following through with your distribution and your FOILing process. All right, and then obviously the same thing for number 4 here. So again, really, really good practice problems for you guys to try on your own here. Moving forward, if we look at the study, okay, if we look at the study here, all right, so when to rationalize the denominator, obviously is when the fraction has at least one radical in it, right? It can have multiple radicals, but regardless, if there's a radical in the denominator, we're going to have to rationalize it, all right? And how do we do that? We multiply the fraction by a form of 1, right? So again, multiplying by that b over b, because if I take b divided by b, I'm going to get a 1 here, all right? And again, I'm going to do this by dividing by an irrational number. The reason I do this is because it's easier to divide by an integer than it is to do that irrational number, right? And we showed that long division process there earlier in the unit, okay? So going through and doing some basic problems here, okay? Hopefully not too difficult. Again, the most difficult part, I believe, is just making sure that you don't lose any factors and that you're doing the proper processes, all right? Then here, figuring out what's the conjugate, right? So again, same exact terms in the same exact order. You just have the difference of sign between them. All right, and then once you figure out the conjugate, okay, you just know that when you have a denominator with multiple terms, you're going to have to multiply by its conjugate. All right, you're going to have to multiply by its conjugate, but still following the exact same processes here. All right, so looking at 2.4 here, obviously we have this checkup, so we'll take a quick look at it, give you a couple hints here. All right, so for these questions, writing the fractions by rationalizing the denominator. Okay, so realizing that all of these here have multiples, so you're going to have to figure out what its conjugate is and then multiplying by its conjugate and continuing that process through, right? Then when we get to 8, 9, and 10, we start to deal with ones that have multiple radicals. But again, you're still just looking for its complex conjugate. Okay, you're still looking for its conjugate there, all right? So hopefully not too difficult, but again, I really suggest you try some of those before you go on. All right, there is one quiz here. Again, this quiz is mandatory, all right? So you have to do this quiz. It is mandatory. Now, this 2.4 journal, okay, this 2.4 journal is not mandatory. This is completely extra credit if you'd like to give it a try here. All right, this is completely extra credit, right? Even partial extra credit you can earn. All right, so again, that sums up 2.4 for us, rationalizing the denominator. Again, you've got the study, the checkup, and the quiz here. And the journal is extra credit if you'd like. On here, lesson 2.5. So this is all about solving radical functions here. All right, so solving radical functions. Okay. And we're gonna look here. It's gonna start off with this roller coaster problem. All right, this roller coaster problem. And you may have talked about this in earlier classes, and if you didn't, not a huge deal here. All right, just remember, don't be intimidated by these unknown equations here, all right? They're just standing for different variables, all right? And obviously this is a math class, so this is all about using those equations, not memorizing or knowing them off the top of your head here, all right? But looking at roller coasters, okay, they have relationships that are similar to polynomial functions, all right? And we're going to find out in this unit, they also have some things to do with radical functions, all right? But the equation that we're going to use for the roller coaster with the radical function is the square root of 2gh equals v. All right, square root of 2gh equals v. And we'll talk a little bit more about this later on, just to remind you. But v will stand for velocity, okay, velocity. G is a constant for gravity, okay? G will be a constant for gravity. And then h stands for height here. All right, it stands for height here. All right, and then obviously it says notice the radicals. So to solve this radical function, we need to apply what we know about adding, subtracting, multiplying, and dividing radicals, right? Again, figuring out what do we have, what do we need, and how can I get there, right? Using the tools that we now have under our belt here. Okay, so then if we look at this, it says to find the velocity of a roller coaster when it hits the bottom of an 100-meter drop here. All right, so all we would do is we would plug in 100 meters for our height here. All right, and then we would plug in our gravity, which is 9.8. Okay, 9.8. We would multiply that out, take the square root of that, and that would give us our velocity there. Okay, that would give us our velocity there. All right. In general, when we're dealing with solving for radical functions, okay, ideally, this is the two steps here. So we're going to isolate the radical, okay, getting the radical by itself on one side of the equation. And we can do that by doing all the processes we already know to isolate variables. Okay, so we're going to isolate that radical, get it by itself, and then we square both sides of the equation. Right, we just square both sides of the equation. Once we've done that, we can simplify through whatever processes we need, if those are even necessary. But let's take a look here at our two examples, looking at these two steps. So first off here, okay, if we look at this first one, step one's already done. The radical is isolated by itself. So all we have to do is square both sides, right? So if I squared this guy, right, squaring undoes our radical. So squaring undoes our radical. So I'm left with just the radicand, which is a value of x there. And then 7 squared gives us 49. Okay, 7 squared gives us 49. All right. Then for the next one here, I have to get the radical by itself, right? Isolate that radical. So I'm going to get 3 to the other side by subtracting. Now I'm going to square both sides, right? Same process here. All right. And then for both of these problems, we're done because we obviously have our variable equal to a number, and there's no other processes that we need to do here. So those are our two major steps. All right. If it's a more complicated radical, right, we still do the first same two steps, isolate the radical, square both sides, but then obviously we add on this third step of solving for our variable, right? So what that looks like here is I've got to isolate my radical first by adding 1 to both sides. All right, now I've got the radical by itself, I'm going to square both sides. Okay, squaring both sides gives me x plus 5 equals 16. All right, and then obviously to get x by itself, we know we have to subtract 5 from both sides, so we're left with x equals 11. All right, so same process for the first two steps and then just one additional step there. All right. Then using properties of radicals. All right, so using properties of our radicals. Okay, we know now, we worked a lot in the beginning of this unit on different ways to combine radicals and to solve for things. So now we're going to use those properties. So for example here, okay, if I have these two radicals divided by themselves, I can combine them, right? I can combine them by putting them under one radical symbol here, all right? So now that they're under one radical symbol, the radical's isolated by itself, I can square both sides, right? I can square both sides, and I'm left with this here, all right? Again, in order to get x minus 1 on the other side, I'm going to multiply both sides by x minus 1. All right, then I'll distribute that 9, okay, and then I can simplify here, right? I can simplify. So getting x on one side, getting all the constants on the other, right? And then dividing out, and I'm left with x equals 3 halves, right? X equals 3 halves. So again, just using the properties at our disposal and then following through the same processes we've been doing for a while now. All right. So here, if we're starting with an isolated radical, okay, we can start with an isolated radical, and we've got x on both sides here. All right, so we're still going to follow through the same processes. Let's square both sides. All right. We'll square both sides, and then we obviously need to multiply this out, our x minus 2 times x minus 2. And if I FOIL that out, this is what I'm left with here. All right, this is what I'm left with. And then I'm going to simplify by bringing this x to the other side, because if I bring it to the other side, look, it looks like our quadratics that we're really familiar with solving, right? I've got my quadratic is equal to 0. All right, so now I know I just have to find the two factors that make up this quadratic. All right, I've got x minus 4 and x minus 1. So I set both of those equal to 0, right? And then I can solve. So I've got x is equal to 4 and x is equal to 1. Right? And if I want to check, all I have to do is plug them back in. All right, and again, this is always an important step here, plugging back in to check, because as you notice here, when I plug them back into my original here, okay, square root of 4 equals 4 minus 2, right? Well, that's 2 equals 2. Perfect. So x equals 4 is a solution. However, when we look at x equals 1, square root of 1 is 1. All right, but 1 minus 2 is negative 1. All right, so square root of 1 equals negative 1. That's not true, okay? That's not equal. So x equals 1 is not a solution. All right, it is not a solution, okay? And we have a name for these false solutions, and they're called extraneous roots. Okay, they're called extraneous roots. All right, and what these are is, again, they are extra things that we think might be the right answer, but when we plug them back in, they make our expression or our equation not true. Okay, so for example here, we had our two solutions. X equals 4 was a solution. X equals 1 is what we call an extraneous root. Okay, it was an extra root that makes our equation not true. All right, so moving forward here, looking a little bit more at extraneous solutions, okay? Again, extraneous, extra, right? Extraneous, you can see the word extra in there, so hopefully that's easy for us to remember here. All right, and again, it's when it makes the equation false, right? So it's an extra solution that is not needed because it doesn't work. All right, so again here, looking at what we just had, we had x equals 4 and x equals 1. So plugging them in, 2 equals 2, great, that one works. Looking at this one, 1 equals negative 1. Well, that's not true, so it doesn't equal this, and this one, again, is our extraneous roots. All right, and they want to point out here, look, when you square both sides of an equation, it is very possible to get extraneous roots. So you should always check answers with this kind of problem, right? So when you have x on both sides, right, or your variable on both sides, it's always a good idea to check those roots, right? And again, in general, I personally always feel it's just a good idea to check your root in general. What's an extra 30 seconds to make sure that you got the right answer? All right. Ooh. So then if we go back here to our roller coaster problem, okay, our roller coaster problem. We'll take a second and read this here. So the giant roller coaster is radical, right? So the formula is used to find their speeds at the bottom of steep drops. Okay, so we can use those to find their speeds. All right, the faster they are, the better they are, right? And what makes a roller coaster travel at top speeds? It's this thing called gravity, right? It's this thing called gravity. And you'll learn more about this principle in physics, but glad I get to give you a little introduction here. All right, so the higher and steeper the hill is, the faster the roller coaster goes, right? And if that's obvious to you, good. Okay, because think about it, the higher the roller coaster goes, the longer it has to pick up this speed as a result of gravity. All right, so looking here, this is how we can develop the formula needed to find a roller coaster's velocity at the bottom of a drop. Okay, and I'm going to fly through this quickly. I just want to give you the introduction as to how you can find this, but this is not the major point of the unit. The major point is using this equation, but let's take a second to figure out how do we figure out the formula for describing velocity of a roller coaster at the bottom of its steep drop. So if we look here, this equation, W equals mgh, okay, this is talking about this thing called gravitational potential energy, all right? And it's a function of mass, gravity due to acceleration, and the height, okay? Gravity, mass, and height, all right? So this W is this thing called potential energy, right? It's as much energy as it could potentially have, right? If you were to reach maximum, all right? But this doesn't tell us the velocity. It tells us how much energy we have, okay, due to mass, gravity, and height. All right, so we need another equation here. And there's this thing called kinetic energy. All right, so kinetic energy stands for KE is equal to 1/2 sorry, 1/2 mass times velocity squared. All right, so if there is no friction lost, right? So if we don't lose any energy due to friction, right? If we have a completely smooth ride, then this W here is going to be equal to our KE, right? So our potential energy is equal to our kinetic energy, right? And potential energy is how much energy you have at the start before you start moving. It's as much energy as you could possibly have. And kinetic energy is our energy as we're moving, right? So assuming that these are going to be equal to each other, we can then make this new equation here, mgh equals 1/2 mv squared. All right, we just set these equations equal to each other. All right, and there's mass on both sides, so we can divide by mass on both sides. So we're left with this 1/2 v squared equals gh. All right. And then obviously we wanted to solve for our velocity. All right, so we multiply both sides by 2 to get the 1/2 away from v, right? And then we need to get v by itself. So again, we take the square root of both sides, right? So again, it's how we get to this formula here. All right, and no, again, you do not have to know this. You just have to be able to use it, right? So that's how we got there. All right, so if we have our velocity, we know it's a factor of square root of 2 times g times h. All right, so again, there's our equation. Just wanted to show you how we got there. All right, but if it has a drop of 100 meters, what's its velocity at the bottom of this drop here? All right, so looking at our equation, like I said, we have 2 times 9.8 because 9.8 is this factor of g. Okay, it's never going to change. All right, that would be something that I would give to you on your test. All right, but we plug in 100 for our h, plug in 9.8 for our g, and then we just solve straight ahead using substitution. So our v value there, we would take the square root. It would give us 44.3. All right, so that would be how we could solve for velocity with a straight ahead problem like that. All right, but what if we wanted to change the height and the velocity? Okay, what if we wanted to change the height and the velocity? All right, so for example, here we look at our problem. A roller coaster engineer is creating his next roller coaster based on one with an 100-meter drop and a velocity of 44 meters per second. Okay, but he wants to increase the height and velocity by the same number x. All right, so basically, what we can do is we can say, okay, well, he wants to go up by a value of x. So all we have to do is add x to both our height and our velocity. So what that looks like here is height was originally 100. Well, we want to add it by a vector of x, right? So plus x. Our velocity was 44. It's going up by the same factor. So that's going to be a plus x there, right? So that's what we're going to change there. All right, so now what we're going to do is we're going to plug in our new equations for our variables here. Okay, so we can plug in our new equations for our variables. So 2 times 9.8 gives us this 19.6. All right, and then I plug in our height here as 100 plus x. Okay, 100 plus x. So we distribute that out, which is how we get here. All right. Same thing here. I have 44 plus x. All right. Once we get down here, we know we need to get rid of this radical. Okay, so we're going to square both sides. Okay, we're going to square both sides. Once we've squared both sides, right, we have to isolate our x variable, right? So we square, we simplify. Okay, we need to isolate our x variable, or the other option is to make it look like something that we know how to solve. So, for example, a quadratic. Boom. Right? So we can have this equal to a quadratic, right? And have the other side equal to 0. So we know that this is our quadratic expression. We know how to solve this, right? This one doesn't look as nice, so we can use our handy dandy friend, the quadratic formula. All right? So when we have the quadratic formula here, okay, we get two values when we solve for the quadratic formula, again, just by plugging in our a, b, and c values. All right, so we get x is either equal to negative 68 or x is equal to 0.35. All right. So first off, we need to check the values, okay, to see if one or the other is extraneous here. So we just substitute them in for h and for v. All right. We substitute them in for h and for v. All right. And obviously here, the velocity can't be negative. All right. The velocity can't be negative. So when we have this negative 68 value, okay, it gives us a negative velocity. So obviously that is not a correct value. So that means that this negative 68.75 is an extraneous solution or an extraneous root. Okay. Also, hopefully something would have rung a bell in your head because we were trying to increase, right? We were trying to make it larger and taller and faster. So why would we add a negative value, right? It wouldn't make sense there. So hopefully you saw that red flag there. But again, you would still plug them in to double check. All right, so our correct answer there would be increasing by this 0.35 factor. All right, this 0.35 factor. All right. Awesome. Okay, so then to confirm what we know here, the first step in solving a radical equation is to isolate the radical. Okay, we need to get it by itself. All right, so using those processes that we already know, get the radical by itself. All right, and then there's plenty of steps for solving, but once we isolate the radical, right, we square both sides, we simplify, and then again, we solve for x if necessary. All right, we solve for x using multiple steps if necessary. Okay. So then here, again, solving, you'd have to isolate the radical. So get 2 to the other side. So minus 2 on both sides. Okay, so you've got square root of x is equal to 8. Okay, so then you're going to square both sides. So 8 squared gives us 64. Right? So that's how you would work this problem. Okay, same thing here. You'd get this 4 on the other side. So you've got square root of 2x plus 3 equals 5. All right, once you do that, you square both sides. And then you've got 2x plus 3 equals 25. All right, subtract 3 from both sides, divide by 2, you get x by itself. Okay, and again, I'll let you try these problems on your own, but hopefully it's not too terribly difficult. It's following the processes, using the principles that we're already really well familiar with. Okay, so again, for this equation, you're going to have to get x by itself first. All right, for this one, same thing. Move 2 to the other side, get this by itself. Once you square both sides, then you solve for this x value here. All right, this one here, before you get started, combine both of these radicals, right? Combine it using that principle. So this is just going to be one giant radical, and underneath it is going to be 2x over x minus 2, right? So once you combine it, then you can square both sides and solve that way. All right, this one here, again, it's already isolated, so you're going to square both sides. All right. And whenever necessary, okay, whenever necessary, you might have to solve a quadratic, okay? And when you get a quadratic, we know we get 2 answers. So make sure you check both of those answers to see if one of them is an extraneous root. Okay, make sure you check both answers to see if one is extraneous. All right. Moving forward here, looking at our study guide. Okay, looking at our study guide. Same thing here. It's a lot of the same repetitive nature, right? So solving the radical, following through with these 3 steps, isolate, square both sides, solve for the variable if necessary. All right. If we have something like this, right, we simplify it using that property that we know. Okay, using the property that we know, we can simplify, then do the exact same thing. It's already isolated, we square both sides, we solve for our variable. All right, and then again, checking for extraneous roots by just plugging them in. Again, an extraneous root is a solution when we're solving for x, but when we plug it back into our original function, it makes the equation not true. All right, so then here, we can solve, get our factor, right? So get our factor of our quadratic using a process that we know. So you can either factor manually, you can factor using the quadratic formula, right? Whatever you know. And then we solve for x. And then all you have to do is check each solution for an extraneous root. So just plug them back in order to check there. All right. So then looking at our checkup here really quickly. Okay. All right. So then for this checkup here, obviously it's just 10 problems here, all about solving. Okay, so all about solving and putting to practice what you've learned. So again, I really suggest you at least do a couple of these. But for all of them, you're going to follow the exact same steps. Okay, isolate the radical. Okay, isolate the radical. Then square both sides. Okay, and then solve for x however necessary. So again, either turning it into a quadratic and factoring from there, or hopefully it's just something easy where x is already by itself, okay? So again, isolating the radical, squaring both sides, and solving using the processes that we know, okay? Again, hopefully not too terribly difficult. All right, for 2.5, there is a quiz. So this is a mandatory quiz here, all right? So far you've got 2 quizzes and 1 extra credit opportunity. All right, moving forward to 2.6, okay? So now we're looking at applications of radical equations, okay? So applications of these radical equations here. All right, so where might these be used in the real world? All right. So first problem here is about a pendulum. Okay, so if we look at a clock here, all right, the formula shown below has the length of the pendulum as a capital L related to time, capital T, swinging back and forth, right? And the time is called the period of the pendulum, all right? So its lengths in centimeters, its times in seconds, right? And it has this period of 2 pi square root of L over 980, all right? So again, please don't get caught up in the equation, right? It's just an equation standing for something. So execute the way you know how to, and then use some logic here at the beginning and at the end when these equations are coming about. So if we start here with our clock problem, okay, a new clock is being built for Newport Clock Tower. How many centimeters long must the pendulum be in order for its period to be 2 seconds? All right, so we want to solve for L in this problem. What words or phrases demonstrates that? All right, again, how many centimeters long? All right, how many centimeters long, right? Or sure, must the pendulum be, right? If we're going to get specific, okay? The centimeters long for the pendulum. All right, what word or phrase tells us the values that we can substitute in T for this, right? Well, right here, its period to be 2 seconds, right? So period is 2 seconds. All right, since again, up here we said T, the time is called the period. Right, so again, using what we know and applying it here. All right, so that's what we would know there. Okay, so if we were then to solve this problem here, okay, we would substitute 2 in for T, since we just found that, right? So we substitute 2 in for T. All right, then we want to get this radical by itself, okay? So we need to get this radical by itself, so we need to divide both sides by 2 pi, right? Divide both sides by 2 pi, so I'm left with 1 over pi equals the square root of L over 980. Okay, now we're going to square both sides, Okay, and then we're going to multiply and get L by itself, and then obviously we can simplify here. And again, remember that pi, yes, it is a symbol here, but it stands for an actual value of 3.14, 159, whatever, yada, yada, yada. Okay, but it is a value that you can plug in and use in your calculator. So when we simplify, okay, it's equal to about 99.29 centimeters long. Okay, so again, hopefully not too terribly difficult. It's just figuring out what you have and plugging in the appropriate places. Taking a look at this next problem here, this is about bridges. All right, so if we use radicals to talk about a bridge here, so let's take a look. We've got two, obviously, bridges, one straight, one's at this kind of upside down V shape, right? So the bridge across Union Bay is 4 kilometers long. In the summer, the bridge expands in length by 1 meter. If the bridge did not have expansion joints, then it would bulge in the middle. Okay, if the bridge bulged straight up, how much higher would it be? Hint, there's 1,000 meters in a kilometer. All right, so if we want to solve for the difference in height when the bridge bulges, what word or phrase demonstrates this? All right, what word or phrase demonstrates this? How much higher would it be, right? How much higher would it be? That's what I would highlight, okay? And sure, they highlighted the entire sentence there, okay? If the bridge bulged straight up, how much higher would it be? That's telling us what we're trying to solve for. All right, question 2 here. If the first step is to draw the diagram, all right, so we have to draw the diagram and label all the lengths in meters. What numbers would we need? All right, well, we know we would need that the bridge is 4 kilometers long, and we know that it expands by 1 meter. All right. Oh, and then sure, right, in the hints, we would also need the 1,000 meters in a kilometer if you didn't know how long those were, right? Again, this is just a conversion factor, getting us from meters to kilometers. All right. So then we can look at this diagram here, all right? So if you look at half of the length of the bridge, okay? Normally, it would be like this, right? Half the length of the bridge in summer. All right, do that expansion, and then half the length of the bridge for the rest of the year. All right, and this would be the height of that bulge. All right. So we can use the numbers given in the problem to calculate 2 half lengths. All right, 2 half lengths. Or for example here, we take the values and we divide them by 2. So if the bridge is 4 kilometers long, half of that is 2,000 meters. All right? Because as you can see here, we are now starting to make a triangle. All right? And hopefully that's ringing some bells here. All right? But if in summer the bridge expands by 1 meter, okay, so that it's 4,001 meters long, half of that would obviously be 2,000.5 meters. All right. So then here, again, we can use this equation. Okay, we can use this equation. And we can substitute in by using Pythagorean theorem. All right, so if we look at this, we've got a right triangle. So Pythagorean theorem says a squared plus b squared equals c squared. All right, so this is my right angle right here. This 2,000.5 is my c squared, right? So I'm left with, I'm sorry, this is my c value here. All right, so they kind of skipped a couple steps here. So this would be c. All right, this would be a, and this could be b. All right, so what this would look like originally is 2,000.5 squared is equal to 2,000 squared plus h squared. All right, and then obviously they took the square root of both sides, so that leaves me with this original value is equal to the square root of both of those squares added together. All right, so then what we could do here is square both sides. All right, we could square both sides knowing that we're solving for h. All right, square both sides. Again, this gives us our original Pythagorean theorem. We can then subtract. Okay, we can subtract and get h by itself. Simplify down first, then we can take the square root of both sides, and we're left with plus or minus 44.73. All right. And obviously there, again, we know that we can't have a negative height. All right, so our height obviously has to be the positive value there. All right, so by expanding just 1 meter, the bridge will have a bulge of almost 45 meters. Okay? So that's how we could solve that problem there. All right, taking a look at the next one here, a toy robot. All right, our toy robot problem. Okay, so again, we're given an equation here. And this is talking about the price and demand of toys. All right, so price and demand, an economics-based problem. All right, so what happens is we've got this equation here where P stands for the price of the robot, okay? X stands for the demand, how many people or what's the demand of people wanting this robot, all right? And this is the equation that we've come up with. So if we look here, the price of a toy robot is related to its demand, the number that can be sold, as shown by the formula here. How big must the demand be for the price to equal $20, all right? So we want to solve for X in this problem. What word or phrase demonstrates this? Well, okay, how big must the demand be? All right, how big must the demand be? All right, so then here, how do you know what the value you can substitute for P in the formula? Well, it says if the price is equal to $20. So we know that we can substitute in for P equals 20. All right, so again, we know that we can substitute in P equals 20, so we substitute in $20 there, right? And then we're going to try to get the radical by itself. So subtracting 35 from both sides, all right? Squaring both sides, okay? Squaring both sides, remember, when you square a negative, it becomes positive, all right? When you square a negative, it becomes positive. So I'm left with 225 equals this binomial here. Okay, I'm going to subtract 3 to get X by itself. All right, divide, and I'm left with X equals 6,342.86. So the demand must be 6,343 toy robots if the price is to be $20. All right, and again, hopefully you notice here that X was the number of toy robots. Okay, and when we get here, even though this value gives us a decimal, okay, we can't have a fraction of a toy robot. So we're going to have to round that up to the nearest whole number. All right, because again, we need it to be at least this many robots here. So we have to round that 0.86 up to another whole robot. All right, so again, be really, really careful. This is where logic comes into play because, like I said, when you go to do these real world problems here, okay, I don't want you to plug in your answer as this value here for X and get it wrong because, again, you can't have a fraction of a robot. So that's going to be something to make sure you're aware of and you're keeping your eye out for. All right, so then here, to confirm the steps for the radical functions, we'll take a look at it. Okay, so identifying the formula function, identify the unknown variables and the known variables. Then we substitute in for the variables that we know. Okay, isolate the variable. If necessary, we can square both sides of the equation to undo the radical, and then we state the answer to our problem. Again, making sure that we're using logic when we're stating the answer, okay? We can't have fractions of whole things like we did for that toy robot problem, okay? So then here, which of these applications is most likely to use a radical function, okay? So this here I think is a little bit trickier of a question right off the bat because it's assuming that you know all these equations here, right? It's assuming that you know all of these equations. All right, so this might be a difficult question here because it's assuming that you know the distance equation, the radius equation, the triangular prism volume equation, all right, and then same thing for the area height triangle question, okay? So this one might be a little bit difficult here, and we can just give you the answer, all right? So the formula for the area of a circle is A equals pi r squared, all right? So since it's r squared there, all right, to isolate r, we're going to have to take the square root, all right? So again, I don't expect you to know these off the top of your head. That one was kind of a difficult question here. But basically, if I gave you all of these equations, right, depending on what you're being asked to find, that's how you would know. So for example here, even if I had this same exact equation, all right, A equals pi r squared. If I asked you to find the area, right? If I asked you to find the area given the radius, you wouldn't need a radical. You wouldn't need a radical because you would just take your r square or your r value and square it, right? So that wouldn't require a radical. The only reason this one is requiring a radical is because we're asking you to solve for r in this equation. All right, so just being really careful with that kind of stuff. All right. And then again, a couple more application-based questions using values. Again, do not let these equations intimidate you. Just figure out what they stand for and then plug in your values and solve using, the mathematical processes you've spent a long time developing. All right. Okay, so same thing here. Which of the following functions is most likely to not use a radical function? Okay. Again, they're assuming that you know all of these equations. So the area of a square, right? That's length times side, right? That's length times side, okay? But this one here, if you have the sides, right? It's like saying L squared. Okay, so to find this one, you would have to take the square root. All right, find the length of a right-hand triangle given the hypotenuse on the other leg. Okay, you're gonna have to take a square root. Given the surface area of a sphere, find the radius. Again, this is that pi r squared. All right, given the length, volume, and height of a rectangle, find the base. All right, I believe it's going to be that one. All right, so again, really difficult here. I understand that. All right, so hopefully there's not too many like that, if any, on your quiz. All right, but again, this is just asking you to be able to know the equations. All right. So if you don't know these equations, all you have to do is go into Google and type in, area of a square and find the equation, all right? Or surface area of a sphere, right? Type that in and it'll give you the equation there, and then you can look and see what it's asking you to do, all right? 2, 3 are asking you again to just plug in values that you know, right? Really evaluate these questions the way that they're given to you. Plug in and solve. All right, so again, hopefully not too difficult. The only difficult part here is really dissecting what those questions are asking you to do. All right, so we went through already, we did the pendulum problem, but again, the trick there is really dissecting what the problem is, filling in the blanks, and filling in for the known values and solving using your processes. Okay, same thing for all of these. Okay, same thing for all of these. All right. So for 2.6, we have a checkup as well, of course. Looking at the checkup here. All right, it's more word problems. All right, it's just more word problems. All right, so again, looking at this equation, taking the time to really read what this is and understand what you're solving for, okay? So again, reading what the problem is, not getting yourself too caught up here with the equations, just using them as is, all right? So again, a lot of word problems, dissecting what they mean, and going from there, okay? For 2.6, you do have a quiz here, all right? This is a mandatory quiz. Now, practice here. This is another extra credit opportunity. So far you have 3 quizzes that are mandatory and 2 potential extra credit opportunities. So, again, take advantage of it if you'd like to get some extra credit, even, again, partial extra credit for partially correct work, all right? Last unit we're going to look at here. So again, we've covered 2.4, 2.5, 2.6. Last one we're going to cover today is 2.7, or this weekend, I guess I should say, is 2.7. All right. So 2.7 is looking at these things called rational exponents. Rational exponents. So let's take a look here. Okay, so with rational exponents, we are talking about radicals. We're still talking about radicals, but we're going to talk about things other than just square roots. Okay, we're going to talk about things other than just square roots. All right, and we'll talk about also exponents that are fractions. All right, we'll talk about both of those things here. So first off, okay, we need to talk about things that are more than just the square root of something. All right, so for non-negative numbers, B and A, all right? So, again, positive for B, positive for A, all right? It says the integer n the nth root of b written as n square root of b is the number that when raised to the nth power is equal to b. I know that is really, really wordy there. Okay, basically what this is saying here is that if you have n root b, all right, that's like saying the nth root of b. All right, the nth root of b. All right, and what it's saying here is I have b to the power of n. I have b to the power of n. Okay. Okay, so I can undo these functions here between the root and the squared by, again, understanding that relationship. So for example here, if I look at example 1, this is saying the third root of 8. Okay, the third root of 8. All right, and that answer is 2. That answer is 2 because 2 raised to the third power gives me 8. All right, 2 raised to the third power gives me 8. All right, and if I took this entire thing here, if I took 3 root of 8, if I had this in parentheses and I raised that to the third power, all right, the third root and to the power of 3, those would cancel each other out. Okay, those would cancel each other out. So I would just be left with 8. Right, so the same way that squaring a radical for square root cancel each other's out, this would be the same thing for the third root here. All right, same thing if we look here at example 2. This is saying the fourth root of 81. The fourth root of 81 equals 3 because 3 raised to the power of 4 equals 81. All right, 3 raised to the power of 4 equals 81. All right, and again, if I have the fourth root of 81 right here, if I take this entire thing and raise it to the power of 4, I'm going to get out just my radicand again. Okay, fourth root and to the power of 4 undo each other. All right, finally, same thing here. Fifth root of 32 equals 2 because obviously 2 raised to the fifth gives me 32. All right, and if I had my fifth root here and I raised this entire thing to the power of 5, that would cancel each other out and I'd be left with just 32. All right, so we can call this positive integer in front of the radical symbol, right, that little n there where it's the nth root, we can call it the index of a radical. All right, we can call it the index of a radical. All right, and the only one that doesn't have a number in front of it is obviously our square root function here. We don't write that 2, so it's assumed that if there's no number, the index is 2. All right, so square root, index 2. At third root, index 3. Fourth root, index 4, right? Same thing for 10 and 25, okay? So that's how we read these, right? And again, if I'm looking at this one, this is the 25th root of 3. All right, the 25th root of 3, and it has an index value of 25. Okay, so we can look then here what happens when radicals are real numbers and when they're not real numbers. Okay, we can look at those values here. Right, so again, knowing the index of a radical is going to be very, very helpful for us because it's going to be able to help us identify what are real numbers and what are not real numbers. So for example here, if we look at radicals that have even indexes, right? So here, 2, 4, 6, right? If it's got a negative radicand, right, there's no value here that when I square it is going to give me a -6, or when I take it to the power of 4, it's going to give me a -1, right? So these are not real numbers, okay? They're not going to be real numbers for us. But if I look at radicals that have odd indexes, right, 3, 3s, 5, 7, right? What I can do is if it can be a positive or a negative radicand, because if I look at the third root of -27, okay, that's going to give me -3. All right, and the reason I can do that is because if I take -3 and I cube it, right, that's going to give me this -27 because the first two, -3 times -3, that's going to cancel those negative signs and that's going to give me a +9. All right, but then I have a third one here. That +9 is going to get multiplied by -3, right? So that's how I get this -27. Same thing happens here with the fifth root of -32, all right? That's going to give me a value of -2, okay? Because, again, 1 and 2 are going to cancel. 3 and 4 are going to cancel. And I'm left with that fifth negative sign. So it's going to end up with a negative final answer. And 2 to the power of 5 is 32. So these guys here are real numbers, okay? They are real numbers when they have an odd index and a negative or positive radicand. All right. The ones we have to be careful with are even radicands and making sure that even indexes to make sure that the radicands are positive values there. Okay. So then what we can do here is we can look at exponents that are fractions, and how this is going to relate here to the work that we've been doing with radicals is that these fractions are actually another way of representing these roots, right? It's another way of representing these roots, okay? So hopefully we already know this. I believe we talked about it, but if we didn't here, okay, square root of n. Square root of n. Another way we can say that is n to the power of 1/2. N to the power of 1/2, right? And in general, we can write radicals as exponents as long as we write them in the fashion of 1/n. Again, where n is the index of the radical here. All right, so for example, my radical's 2, okay, so I'm going to say 25 to the 1/2, right? That's the same thing as saying square root of 25, right? And regardless, they're both going to give me this answer of 5. They're both going to give me this answer of 5. All right, if I look here, I've got the third root of 64. That's like saying 64 to the power of 1/3. All right, again, my index is 3, so I write it as 1/3. That's going to give me a value of 4 there. Okay, it's going to give me a value of 4. Reason is 4 cubed gives me 64. All right, same thing happens for an index of 4, index of 6. It's going to be the exact same. All right, it's going to be the exact same. So it's like saying, again, whatever our radicand is, okay, to the power of 1 over our index value. All right, 1 over our index value. All right, so now if we confirm here just what we've learned, okay, we learned about index of radicals, we learned about how important they are and how they can help us write our radicals as exponents instead. All right, so the positive integer n in front of the radical sign, okay, is called the index, right? So n is our index value, and this is like saying the nth root of b. All right, nth root. Okay, so that's, again, just saying that another way of reading this. So n root of b is like saying the nth root, again, where n is our index value. Okay, and then determining if radicals are real or not. That's going to be based on what the index value is. If the index is positive or even, or I'm sorry, positive or, goodness gracious, if the index is even or odd. All right, if it's even or odd. All right, for odd number indexes, it doesn't matter if the radicand is positive or negative. They're going to be both real numbers, okay? But when you have an even index, this is where you have to be careful. If you have an even index, again, you cannot have a negative radicand because we have no known way of getting a negative value when it's an even index. All right, so knowing this is going to be super helpful here. All right, so then moving forward, all right, simplify the expression. So this is like saying 27, and we take the cube root of it. So what's going to give us the cube root of 27? All right, what's going to give us the cube root of 27? That's going to be 3 there. All right. So again, knowing how this is written, okay, you can do multiple things. So in your calculator, you can actually put things to the power of fractional exponents. So if you write in your calculator 27 to the power of 1 divided by 3, it will give you out the answer of 3 here. All right, it will give you out an answer if there is an answer to report. All right, so you can actually just plug this straight into your calculator the way that you see it. Or if that makes you uncomfortable, as long as you understand how to go from 1/3 to, again, this is being the third root, all right, you can do that as well. All right, same thing here. If you don't know how to put in the 5th root of 12, you can put in your calculator 12 to the power of 1/5. All right, 12 to the power of 1/5. You can do that. All right, so I'll let you try those questions out there. All right. Here, what fractional exponent represents a cube root? Fractional exponent, so that's going to be 1 over 3 here. All right, again, remember, it's 1 over the index value. Simplifying this expression, again, this is saying 32 to the 1/5 power. That's like saying the 5th root of 32. All right, the 5th root of 32. Okay, this is knowing your index values. Okay, so remember, if I have negative radicands, it can only be odd number indexes, right? It can only be odd number indexes. So 1/3 or 1/5, right? Those are indicating odd indexes. All right. Which of the following is the index of a square root? Okay, square root, that's going to be 2, right? Just because it's not there, when we have our radical symbol, it's still an index of 2 there. Okay, so then looking here at more rational exponents. So we've pretty much only seen them in the form so far as 1 over n, right? Again, n being our index value here. All right. In general, though, okay, we can show them as m over n. All right, m over n. N is still going to be that index value of our radical symbol. However, m is going to be an exponent. And so what we can see here, and I'll zoom in so it's a little bit easier. All right, m is actually what we raise our radicand to. All right, so if I have b is m over n, it's like saying b to the power of n times by 1 over n, or the nth root of b to the power of m. All right, the nth root of b to the power of m. All right, and if we look at these examples here, all right, this is 4 to the power of 3 halves. Okay, that's like saying 4 cubed, and then we take the square root of it. So you can do this in the steps that they have it, right? So you take what is 4 cubed? Okay, 4 cubed is 64. Okay, then we have 64 to the 1/2. We take the square root of 64. That gives us 8. All right, we can do that. If you look at example 3 here, 8 to the 2/3. So that's saying 8 squared, and then we're going to take the cube root of it. All right, 8 squared gives us 64. 64 to the 1/3, or to the cube root. All right, that gives us 4 there. All right, so I know it's a new way of seeing it, but again, it's just adding on a little bit to what we know here. So now, instead of always having a 1, if we have an m here, we can take our radicand to the power of m. All right. Another way of simplifying this here would be to do the opposite process first. All right. So what we could do is, instead of taking and taking to the first exponent, right, taking it to the m power, we can do our radical first. All right. So what this is saying here is we can find our nth root and then raise it to the mth power. So for example here, 4 to the 3 halves. Okay, so we can take the square root of our 4, right? That gives us 2, and then we can take 2 to the 3rd power, which gives us 8, right? So we can do our taking to the nth power first, or we can take our radical first, right? It's whatever's going to be easiest for you, or whatever works out based on the numbers that we have. All right, if we have 81 to the 3/4 here, all right, I can easily take the 4th root of 81. That's going to get us down to 3. All right, so then I'm left with 3 cubed. That gives me 27. All right, and then same thing here. Obviously, I have 8 to the 2/3, so taking the 3rd root of 8 gives me 2, and then I can do 2 squared, which gives me 4. All right, and again, the way that you're going to know which process to do, or the way that I know which process to do, is I always look at my roots first. Right? I always look and see, okay, so I can look at 4, and I know I need to do the square root of 4. All right, the question is can I do the square root of 4 off the top of my head? And the answer is yes, I can. right? So that's an easy one and it works out well for me. All right, so I would do that first before I do the cubing. All right, and that's just a personal preference here. But you can do either way. All right. Looking here then, we can move even further to these things called decimal exponents. All right. So you might see a fraction written as a decimal. All right. Now, what the three steps are to solving this is write the decimal as a sum of rational numbers. Okay, write it as a sum of rational numbers, split it up into a product using the multiplication properties of exponents, and then we're going to reduce the fractions. All right, so let's see what that actually looks like in real world here. Okay, if I have 5 to the power of 2.46, all right, I'm going to change that decimal to a fraction. All right, I'm going to change that decimal to a fraction. All right. And I don't know why they did it like this, right? But you could in your calculator, right? You have the ability here to change decimals to fractions. It's underneath that math tab, right? It'll say decimal to fraction, or it should say D arrow F, which means decimal to fraction. Okay. But if you were to split it up like this, okay, obviously we know that this is 4 over 10 or 4/10, right? And this is 6 over 100. Or another way of saying this is 40 over 100. So this would be 46 over 100. All right, regardless though, if this is what we get as our fraction, we can split it up. All right, so we carry the 5 throughout all 3 of these. Okay, we carry the 5 throughout all 3 of these. And remember that when we multiply things with the same base, right? When we multiply things with the same base, so this is base 5, base 5, base 5, we add them together, all right? So if we were starting here and working up, that would be why we can add those guys together, because they have the same base, so we're going to add them, all right? So we can use that process in the opposite direction, so we can split these up. So since these are added together, I am going to multiply them with the same base, all right? So then I can reduce each of the exponents. And I can reduce them down. So 4 over 10 goes to 2/5. 6 over 100 goes to 3/50. All right, I can reduce those fractions. And then obviously the next step here would be to solve each of those individually and then carry out the appropriate processes here. All right. But when we're confirming this here, when we evaluate our expression b to the m over n becomes the index of the radical. Okay, it's still the index of the radical. M because what becomes whatever we're raising b to, right? Whatever we're raising b to. Okay, what is the rational exponent? All right, that would be our m over n. All right, and then the decimal exponents, okay, we would write them as a rational exponent by converting it to a fraction, all right? And again, if it's an easy fraction that we already know, right, like 0.25, we know that's 1/4, right? So going through and just changing that to our 1/4 there. All right, if it was something more complicated like that problem, we could split it up and use the properties that we know here. Okay, so again, looking at this 4 to the 2/3. All right, so this is saying 4 squared, and we're going to take the cube root of it. All right, so 4 squared, and we're going to take the cube root of it. So that would be letter B there. All right, letter B. Another way would be letter D. Okay, we can also take the cube root of it first and then square that. All right, so it would be choices B and D. All right, choices B and D. Looking at this, again, knowing that we can do either of those processes first, all right, we're going to go through and do this and then simplify our expression here. All right, so for me personally, I would take the 4th root of 16, right? I would take the 4th root of 16 and then I would raise it to the 5th power. All right, but I'll let you do that on your own there. Okay, so then equivalent pairs here, showing the equivalent pairs. So this is 5 halves, 3 to the 5 halves. This is like saying the square root of 3 to the power of 5. Square root of 3 to the power of 5. Perfect. All right, 6 in the 4/3. All right, so this is saying 6 to the power of 4 and taking the third root of it. So not this guy. Those are flipped. All right, 8 and 5/3. So again, to the 5th power, taking the third root of it. So A and C so far. All right, and then lastly here, D to the 3/2. 27 to the 3/2. So again, this is saying to the power of 3 and taking the 5th root of it. So not D. All right. Again, simplifying the expression by doing whatever processes you want first. Same problem here for 3. And for 4 here, okay, what's the equivalent expression? All right, and so in the way that they have it written, it would be letter B here, all right? Because again, if I multiply things together with the same base, I'm going to add up the exponents. I'm going to add up the exponent, so it should be letter B there, all right? Because you add up the exponents. Looking at our last study guide here, quickly. All right. Again, understanding what the different parts are. You've got your index, you've got your radicand, all right, which means that I can raise this to the 1 over n power, all right, 1 over n power, all right. Understanding here that if I've got an even index, only positive radicands can be real numbers, but when I have an odd index, both positive and negatives can be real numbers. All right, again, writing n root of b is also like saying b to the power of 1 over n. All right, solving some problems there, and then understanding that now we can write it as m over n, right? M over n, where we're going to take our radicand to the power of m. Okay, and we can write that in 2 ways. Either taking our radicand and bringing it to the n power and then raising it to the 1 over whatever our index is, right? So basically, essentially taking our exponent and then taking our root, or we can take our root first and then raise it to the exponent, right? Either method works, all right? So again, using either method, figuring out what we can do easily here. All right, and then finally, that last little bit that we worked on was changing it to a decimal. So again, this is if you have something that's not as easy, right? Not as easy. So we had 5 to the power of 2.46. All right, 0.46 is not a really nice fraction, but you would follow these steps and it could break down really easily. All right, again, if you had something like 5 to the power of 0.25, you know that 0.25 is 1/4, so you don't have to go through this entire process here, okay? So then looking finally here, we have our checkup. All right, so our checkup is going to be a lot more practice problems for us. All right, again, just simplifying the expression using either method. All right, so either taking it as you see it here, so taking 25 squared and then taking the 4th root of it, or getting to decide for yourself. All right, getting to decide for yourself. And then finally here for 9 and 10. For 9 and 10, these are really, really good problems for you to work on, okay? It is order of operation, okay? Order of operation. If we look at number 10 here, okay, you could do one of 2 things. You could solve it the way that you see it here, all right? And I don't know if we've talked about this before, but if you have a fraction, or if you have a exponent raised to an exponent, so if I delete this here, you have an exponent raised to an exponent. What you can do is you can multiply those exponents together. All right, so that's what they do, is they multiply those exponents together, and you can simplify, and then you're just left with 2 to the power of 3. All right, same thing over here. You have an exponent raised to an exponent. You can multiply those guys together, simplify, and it's much, much easier. All right. Or if that's confusing to you, you can do order of operations, but it'll get really complicated really quickly with the numbers that we have here. All right, so you could do 2 to the power of 6 over 4, right? You could take 6 to the power of 4, 2 to the power of 6, wow. You could take 2 to the power of 6 and then take the 4th root of it and then go through the process, raise that number to the 8th power and then take the 4th root of it again, right? Or you could just do our shortcut method of multiplying those exponents together, All right, so again, when you have an exponent raised to an exponent, you can just multiply those exponents together. All right, and then finally here, being careful with order of operations, again, is important. So exponent raised to the exponent. So we just multiplied those together, and this gives us 5 to the power of 2. All right, and they were really particular with putting the parentheses first, okay? Because you're going to take 5 to the power of 2, then you're going to take the negative of it. All right, so you take 5 to the power of 2, then you take the negative of it. It's not saying negative 5 squared. It's saying 5 squared and then take the negative. All right. So to finish this one off, we have 2 quizzes here. All right, so fractional exponents. This is starting with part 1, and then fractional exponents part 2. Okay, so again, if I was a betting woman, I would say this is about 1 over n, and this one's about m over n. All right, so again, just to remind you, 2.4, you have 1 quiz, 1 extra credit opportunity. 2.5, you have just 1 quiz. 2.6, you have 1 quiz, 1 extra credit opportunity. And 2.7, you're going to end with 2 quizzes here. All right, we're going to pick up Monday's class with 2.8, 2.9, and then your unit test for 2.10. All right, so that's what we're going to cover on Monday. So try to get those 4 lessons done this weekend, and then, of course, always let me know if you have any questions for me. All right, awesome. Then I will see you guys on Monday, and we will finish up Unit 2 on Monday.